Hi now, how are you? So we're going to illustrate some of the illustrations that you can present in class. So we're, say, going to find error correcting machines, which correct one-bit errors. This is a typical example. So suppose somebody wants to transmit 0101 through a medium, and Jove is equipped to handle regular expressions, which is a module that we haven't looked at yet, but it is quite easy to see that the 0 plus 0101 can be corrupted by either changing this 0 to a 1 or changing this 1 to a 0. And we want to generate a Hamming distance 2 strings with respect to the enclosing context. So it is easy to see that if I do 0 or 1, 0 or 1 in the first two places, it actually allows for 0 errors, 1 error, or 2 errors. So 0, 1, 0, 1 is no error. 0, 1, 0, 1, 0, 1 is 2 errors, etc. So these regular expressions exhaust the possibility of 2-bit errors in any of these. So let us make a regular expression, and that is the regular expression. You can print it out, and we can get the minimal form for the machine that is obtained, and that is the machine that does 2-bit error correction. And if more than 2-bit of errors are encountered, the machine crashes out. And let us see. This is okay. So let us see how it accepts. And the unmentioned transitions go to the black hole. This is accepting modulo 2 errors. So 0, 1, 0, 1 is an acceptance. 1, 0, 0, 1 is an acceptance. So is there more hidden here? So let us look at that. And this is the dot object with black hole. So show me everything where it crashes out and shows it. And I think it is fully decoded. So in that sense, it is showing all the cases that needs to be shown. Okay, so that's how it is. Now, how to introduce the same idea using non-deterministic machines, which is, again, a chapter we haven't shown. So basically, in the non-deterministic machine, you can introduce layers of transitions, and I'll show you that. So this is how the non-deterministic automaton for the same problem looks like. 0, 1, 0, 1 is accepted. 1, 0, 0, 1 is accepted, etc. So this actually contains the acceptance for all 2-bit errors that you can see. There are some missing transitions here. So what happens if there is one transition here? So let us see whether that is present here. Dot object NFA, and this is the dot object NFA. This is the dot object NFA. So the NFA is being shown, and NFAs, of course, can leave things unexpanded. Here, of course, I was seeing whether the missing transitions are mentioned, 0, 1. And so how about 1, 0, and then 0, 1, that is accepted. 1, 1, 1, 1 is accepted. How so? Because you can actually put these two as the errors. Okay. So in that sense, this machine is complete. I didn't realize that. Now you can actually see. So it is essentially the length of 4, and then 2 bits are allowed to be marked up with. Okay, so anyway, we arrived at the NFA and the regular expression for the same problem. And you have 2 NFAs present, or 1 NFA and a minimal DFA. So now you can see, did I get the same problem solved in identical ways? So you can actually take this NFA and then subject to NFA to DFA and minimize. And lo and behold, this machine starts looking like the one that you got through regular expressions. And now you can see whether the machines are isomorphic, and indeed they're isomorphic. So the exercise actually is one where you state a problem of strings that are a certain Hamming distance away from a given set of strings. Of course, regular expressions are being altered to model the amount of error allowed. And then you can directly convert that regular expression. But you know that regular expressions are sometimes tricky and error prone. So the user might like to design an NFA, which is well documented, and it actually starts by saying 0, 1, 0, 1 is allowed, but any one of these variations is allowed. If instead of this 0, you get a 1, you are essentially going to continue like the trajectory above because you suffered a trajectory, an error of that kind. So after 2 errors, you had to follow 0, 1. That is the idea. So here you have to totalize the machine, then only you will see the missing transitions. So this is the dot object of NFA, and minimal DFA. I was able to totalize it inside and things like that. So 1, 1. So basically 1, 0 is the erroneous case, 2 errors, and 1, 0, and then 1 should be an error. 1, 0, and a 1, and 0 is and then there is a 1. Okay, so the real I hope you can decipher this one a little bit more. The way it is stated, 2-bit errors need not crash out right away, because look at this: 1, 0, 1, 0. It has not accepted that. But remember that the starting context was given to be 0, 1 star. So you could have any garbage absorbed here and then situate the actual problem pattern later. So try leaving the leading and trailing patterns out and just focus on just the 4-bit pattern and see whether you get slightly different behaviors. All these are up to you. So essentially, all I showed is that thinking this way and thinking through non-deterministic machines with the same thought expressed, you can see the 0 plus 1 star, 0 plus 1 star, and then the pattern of 0, 1, 0, 1 in between with 2 corruptions allowed matches the regular expression notion. Okay, so thank you. And this is a little module that simply focused on error correction. And we'll come to another module that will record another amusement problem or another serious problem based on how you view the world. So after that, we'll look at regular expression, NFA to RE, and things like that. Thank you, and see you next time.